All right. So you'll note I changed the title. It was Teaching Workflow Systems to New Users. Why is it so hard? And I decided to change users to graduate students, and that's because that's really what my talk is about. I think the lessons translate to users in general, but happy to chat more about exactly why grad students are a unique blend of challenges. Maybe that's not the right way to describe graduate students, but anyway, you get the idea. All right. So I'm online in various places. Please feel free to reach out. My email response time is somewhere between 5 milliseconds and 3 years. So don't get your hopes up, but sometimes I'll respond. Filing issues turns out to be a better way to get a hold of me, and I'll talk a little bit about that in a sec. Yeah, so I'm a professor at the School of Veterinary Medicine here at UC Davis, and I work on lots of different things, and I'll introduce myself more in a little bit. But I'm going to talk today about SnakeMake, and I wanted to give you SnakeMake in 2 slides for those of you that aren't familiar with it. There'll be more slides of SnakeMake, but it's not really about SnakeMake per se. So SnakeMake, snake files consist of my preferred workflow system is SnakeMake. Snake files consist of a set of recipes. Here we have a recipe for applying the sour mash software to a genome, sketching it, and producing a .sig file. That's what the first recipe does. It says, given this file, you can produce this output by running this command, and it will replace input with whatever's here. It will replace output, if it were to show up, with whatever's here. Here, the output is actually inferred. Sour mash just makes this output by name by default, but you can also specify it. Compared genomes is something that takes in, the rule compare genomes is something that takes in multiple of these signatures and produces a single file as an output, and then plot comparison takes that single file as input and produces a single file as output. If you've used make, if you use Nextflow, if you've used, shell scripts, all of this should be sort of fairly straightforward. The cool thing here is just the SnakeMake will automatically figure out the value of accession. If you ask for an fna.gz.sig file, it will automatically fill in accession here and run this command for you. And so you can sort of request whatever set of files you want. So this is the recipe side of SnakeMake. And then the other side of SnakeMake is what I call concrete rules. This is my own definition. And concrete rules are literally just what you want made. So there's a bunch of rules telling you how to make certain things. And then here you say, well, I want you to actually make these 4 signature files. So fill in ACK in this rule using the expand command, fill in ACK in this rule with all of the values here, so that compare genomes now compares all 4 genomes, which are automatically built, the sketches for which are automatically built here. So that's my SnakeMake in 2 slides. It's Python syntax, so the quoting and the tabs and so on are all Pythonic, and you can get syntax highlighting and stuff if you use the right editor. Okay, so here I just want to say, SnakeMake is clearly the best workflow system for biology. It's got a big community, a lot of users. You should just use SnakeMake. And I'm not really interested in arguing about this, so don't at me in on discussions. That's a joke. There are many workflow systems. I think Michael Crusoe has a list of probably up to 140 or 150 by now. I would just say SnakeMake's not a bad workflow system for biologists to use because it's got a big community, it's got a lot of users. It's integrated with Python, so you can use the best programming language in the world to extend SnakeMake, unless you're also using Rust, in which case, it's a tie for the best programming language. SnakeMake is really fantastic for what I call exploratory research workflows. I'm building my workflow as I figure out what my question is, and I need to add all sorts of ancillary things, and I just sort of want to accrete workflow rules as I go. Nextflow is also fantastic. CWL and WDL are excellent options for production systems where you need to run hundreds of thousands to millions of jobs, and you want something that's a little more, not sure what the right word is, a little more suited for scale than SnakeMake, at least. SnakeMake starts to bog down once you get past between 10 and 100,000 jobs. It starts to become tricky. So I dropped my slides into my lab Slack this morning asking for hot takes, and one of my grad students responded with 2 memes. So here's Bernie Sanders telling you, embrace SnakeMake, or at least workflows of some kind. I'm not particularly picky about which workflow system you use. Just please use one. Okay, so one really big problem with SnakeMake is that, frankly, it's hard to learn. And the documentation is pretty good, but you already have to be computationally expert in order to understand what you want to do with how you want to use all the snake syntax. So one solution, I'm not going to call this a solution, one work in progress is in 2023, at the tail end of the COVID lockdown stuff, I started writing a book on SnakeMake, and it's called An Introduction to SnakeMake for Bioinformatics, and you can go read the book draft there. And I sort of got, as with many such projects, I sort of got 40% into building the infrastructure, 20% into building the text. It's freely available. I've written the several blog posts extracting information from it, and maybe one day I'll finish it, but I've been told people like it as an introduction. But that's not how I teach SnakeMake. So, and I'll tell you how I teach SnakeMake in a sec. So why do I care? What do I do? Who am I? So I'm a professor here at UC Davis. I'm one of the bioinformatics generalists on campus, which means that basically when new graduate students or new postdocs come to campus and they're like, how do I use the computing system? How do I do my variant calling? How do I do my various bioinformatics tasks? One way or another, they often end up in my inbox or in my classes or in my workshops, and I would like to help them do their jobs. I'd like to help them do bioinformatics at scale. And so that's where a lot of the motivation for all this comes from. I'm also an open source Nick. I like to openly develop and maintain software. I'm really interested in fostering a good open online community. That is also, of course, always a work in progress. Um, I have taken on the role of one of my main jobs these days is the support and maintenance dude, it's like to call it, for Sour Mash, which is software that um, does really massive scale bioinformatics sequence analysis. And in some sense, I'm working through the challenges inherent in the question, can a senior professor also be an actual functional open source maintainer? And so this is the joke that if you email me about how to use Sour Mash, you're less likely to get a fast response than if you go on our issue tracker and post something, because I really like answering a question once and for all in public. Whereas email, I send it to somebody and then I have to send the same response slightly modified to someone else later on. So our issue tracker is some combination of a gem and also a terrible disaster of responses and stuff. And I think there's probably a research study in there somewhere about long-term issue trackers and how they can be valuable and how they can be challenging. So, but SnakeMake. So that's sort of my background, and so back to teaching SnakeMake. So I often start. I teach the Intro Bioinformatics grad class here for the Genetics and Genomics grad group, and I've tried two different approaches to teaching SnakeMake over the last 5 years. Let me take a step back. About 6 years ago, I was teaching the class, and I became really unhappy at teaching variant calling. So this is where you take a pile of shotgun sequencing reads and you match them to one or more reference genomes, and you look for differences between what you sequenced and what's in the database. And it's something that essentially every biologist ends up doing at some point in their life these days. And so it seemed like a good motivating thing to teach, to get people into computing and bioinformatics. And the problem with it is that you end up having to run about 8 different commands in order to get your first result. And if you teach people how to run the commands at the shell prompt, they're basically end up copying and pasting 8 commands. You can give them a shell script, but then it's like a black box that they have to unpack, and that's annoying. So I decided 6 or so years ago that I would teach people what I thought they needed to know, how they should be doing bioinformatics in 3 to 4 years, not how we actually necessarily did bioinformatics when we started. So I decided to teach SnakeMake, and I tried 2 different approaches over the last 5 years, and I would say both of them have failed. They're good starts, but work in progress. And so the 2 approaches, one is inductive, and the idea here, I'll show you examples of this. We start with some shell commands and then slowly decorate the shell commands and generalize as we go. The other is sort of the more traditional deductive approach, where I say, your job is to build a workflow. Here's how you build a workflow. Here's what a workflow looks like. Let's add features to the workflow. And you build a workflow progressively. So here's an example. The first slide shows the first thing I show the students when they show up in class for the inductive approach. I give them a bunch of rules and I say, hey, there's a rule called uncompressed genome. And when you run the rule uncompressed genome, it uncompresses this GZ file. And then when you run the rule, and the next thing you need to do is index the genome for BWA for mapping. And when you run the rule index genome BWA, it runs this rule. So this is basically like a shell script, but in snake file form. And then you have to like tell SnakeMake run this rule, then run this rule, then run this rule, then run this rule. And they sort of get the idea like these are all commands that I need to run. And they're sometimes complicated and they're sometimes easy. And you could get all of this from Googling or from ChatGPT. So the next step is I say, okay, well, the cool thing is we can actually decorate these rules with information about what they take in and what they produce. And then the nice thing is they will SnakeMake will chain the rules for you. If you say I want to map reads, it will say, oh, I need this fast QGZ file. I need this AMB file. Okay, to get this AMB file, I need to have to run BWA index on this file. To get this file, I need to this file, which was produced by running this command on this file, right? So it's the dependency chaining, the DAG that makes workflows so useful. And so I teach them this. And then at some point I come in and I say, okay, well, now if you put curly braces around all these things, you can get SnakeMake to fill things in automatically. So you don't need to add new rules. You literally just need to say, SnakeMake, bake me a cake. And it will figure out, all of the things, right? And so I do this over a period of 4 weeks. And I teach people, graduate students are sitting there and they're learning about our HPC system. They're learning how to log in. They're learning how to use an editor. They're learning how to run commands. They're learning how to use Conda to install software. They're learning about data files. They're learning about failure, all of the fun computational things that we all suffer through. The other approach is just I just have an outline of, but it's pretty normal. It's sort of the default way you would think about teaching SnakeMake, I think, or teaching anything computational. It's like log in, get some files, run Snake, fill in a file, run SnakeMake, make some changes, test it locally by making another copy. So I'm showing them sort of the GitHub dance, and then we add some new things to sort of we add some default rules and so on and so forth. So this is sort of and then we learn to use SnakeMake wildcards and glob wildcards to import file lists and so on and so forth. So this is sort of, I call this deductive because it's like you come in already knowing you, or just having been told that you want to learn how to write a snake file, and then I give you a snake file and you then start adding features to it. And I do this. This is when I teach SnakeMake in a single 3-hour session. So I don't know if either of these approaches work. It's actually really hard to know long-term what impact you have when you're teaching. Some people seem to get it. I'll just say teaching grad students this stuff is really hard. And it takes practice to get good at this. One of our big problems, I think, at UC Davis, and I think this is generally true of grad school, but UC Davis has a particular structure that makes it particularly difficult, is that bio grad students usually aren't doing real research until their third year. And we're teaching them all of this in their first year. So they don't know why they need to, they barely know why they need to use computers. They certainly don't necessarily know how to use computers to do anything they're going to do for their research. And so I teach them the stuff, and then by their third year, they've forgotten it all, and they're sort of only vaguely aware that SnakeMake or workflow systems even exist. And they're usually bogged down in the details of their data, and their advisors sending over them, flogging them with, hey, we got this data and it cost tens of thousands of dollars. Where's the answer? Where's the answer? Where's the answer? And the idea of taking a step back to learn to do something more efficiently is a hard sell. But anyway, that's the best. Those lessons are the best that I can do in the first year. And every now and then I get that wonderful result where a third year or fourth student comes back and says, actually, I now get it. I get why you taught us that. That was really helpful. Now that I'm in my fourth year, you weren't actually a terrible teacher. Usually I don't say a terrible teacher, but they say things like, I didn't understand why you were teaching it us. I don't understand why you're teaching us this at the time. It seems like you're teaching us these useless things when what I really want to be doing is analyzing my data. And I'm like, well, I have some bad news for you about what actually analyzing data looks like. But trust only gets extended to you so far by grad students in grad school, which is appropriate. They should be figuring things out for themselves. So, the whole point of this talk, why is this so hard? We all have reasons. We can all list a lot of reasons, but my sort of unifying theory, or at least a unifying theory for me, is that workflow systems are really a mirror of our computing landscape, and our computing landscape is complex and capricious. So, basically almost every feature in our workflow systems exists because our computers kind of suck. And, I love computation. I love Unix. I love programming. I love all of this stuff, but like a lot of it's pretty arbitrary. And I'll talk about that in a second. So, okay, my favorite example of this, exit codes. So presumably everybody here knows when you run a command at the Unix shell, you don't know if the command succeeded or not. You have to examine the exit code. And if the exit code is 0, that's the universal signal that the command succeeded, or at least The program doesn't know that it failed if you get an exit code of zero. Yeah, like these double negatives. And so workflow systems, so often you run a command and it fails invisibly, or it succeeds with a lot of error, with a lot of output, and you can't read 1,000 lines of output to figure out whether that was a fatal error or not. So you have to examine the exit code, and this comes up a lot in shell scripts. Shell scripts basically, unless you set a particular variable configuration parameter, shell scripts will just keep on going when commands fail. And you can use something like set -e, but then every time you use certain shell programming idioms, they fail. So it becomes sort of a complicated situation. Regardless, I would just say like this is generally a huge problem for newbies. I can't tell if my script succeeded or failed. And SnakeMake, like any good workflow system, will say, hey, dude, your command failed. I'm going to delete the output because any output that exists because probably it's not legit. And it took me a couple of years to realize that part of a major reason for me using SnakeMake was I just no longer had to worry about this. It's like the sense of psychological safety blanket. The SnakeMake would alert me when a command actually had an exit code that was fail. And so, why exit code of zero? So it turns out if you dig into why exit code of zero is cool, it means good things. You can go do some research and you can't figure out why. My best guess is that it's because zero is a good singular value, right? It's either zero or some arbitrary number. And it's nice to have zero be meaningful and then all the other numbers all be wrong for different reasons. So, right, you get different exit codes and they sometimes mean something depending on the program running. But I have been unable to track down why zero. So then, so I have a whole section in my book for like why you have to worry about exit codes and how to make things work in non-intuitive situations. For example, something I frequently run into in one of my classes where I show people how to subsample their sequencing data set so that their commands run in a reasonable amount of time is I run this command gunzip -c large file.gz, and then I take off the first million lines with head. This actually returns an exit code, a non-zero exit code on any large file because head will stop accepting input. gunzip will try to write output and it will fail to write, and gunzip will say, oh, that shouldn't happen. And then your shell command will fail and SnakeMake will fail. So if you actually want to write subsampling into your snake file, you have to put an or true at the end of this command. And this mystifies students. So I wrote a whole section on it. Yeah. Okay. So Unix is somewhat arbitrary and capricious. I love Unix. It's arbitrary and capricious because choices need to be made. They were made 60 years ago, 70 years ago. And now we're dealing with the consequences of those choices, and maybe we'll be dealing with them another 1,000 years. There's a fantastic book by Werner Vinge, Deepness in the Sky, where this person's on a ram scoop traveling interstellarly, like traveling between stars. And he's awake. Normally people go into sleep, but there has to be a watch maintained. And he notices that there's a timing bug that's throwing off a lot of their arrival details. And it's because they're running Unix. And he has to dig several layers down to figure out that all the patches on top of the patches on top of the patches to deal with relativity have a bug in them, that traces back to like code that was written in the early 2000s or late 60s or whatever. It's just really challenging to teach all of this stuff, right? So there's back to Unix in general. It's really challenging to teach all this stuff. And I put this in because I knew there'd be a bunch of people in the comments or in the chat telling me, but these are really important decisions. Yeah, there's a reason for many of these decisions. I can intuit or infer or even know sometimes why these decisions were made. They're good decisions. You can't figure them out from first principles, though. So they need to be taught. And there are deep principles underlying computing, but it's really hard to teach all this stuff to a newbie because it presents as a collection of details. And the newbie's like, I can barely type fast enough to do things usefully. And now you expect me to remember eight flags for ls, which all tell me different useful information. That's just crazy. Okay, so the implications of this theory that workflow systems are a mirror of our computing landscape is that, maybe if we could teach a workflow system properly and thoroughly, people would come away with a more in-depth understanding of how computers work. And maybe a really good book on SnakeMake could actually be a really good book on practical computing. Was part of the motivation for writing the book. And I personally think this would be pretty amazing. I don't care who writes the book, somebody else can write the book, but we need a better way to teach practical computing than we currently have. The way we teach practical computing right now, at least to graduate students, is to tell them, hi, I'm your advisor. You're going to generate a lot of data. You're going to analyze it, or else you're not going to get your PhD. Good luck. Here's all the campus resources. And I feel like it works out surprisingly well because graduate students are amazing and smart and hardworking. But I feel like maybe there's a better way. So I don't know. That's my theory number one. Theory number two, or challenge number two, how do we decide what order to teach things in? As soon as you start trying to design a bioinformatics course, life gets difficult. There's basically no principled approach to teaching practical computing, as far as I can tell. There's no concept inventory. There's no standard textbook. I know you all have your opinions. I'm sure you've all taught this. I'm just telling you, it's not straightforward. So how do you decide what order to introduce concepts in? The best that I've found is to teach based on what people already know, which usually you have to guess at because people don't know what they don't know. But then this turns out to be really heavily path dependent and hence individualized. So I get graduate students that have a great background in stats and physics and have hence used the command line a fair bit, but they know beans about biology. And then I have biologists who are like, I get DNA. I just need to know the 5 commands to go from my shotgun sequencing to my results. And you have a class with both of those people in there, and it's a recipe for uh, unhappiness. So my theory number two is that we should design computational training based on what I call Kernighan's principle, which is something I made up. And so I don't know how many of you are familiar with Kernighan's law. Kernighan's law was stated by Brian Kernighan, one of the creators of Unix and the C programming language in 1974, incidentally the year I was born, which is a different comment. Everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? And I'm guessing any of you that have written clever scripts or programs have run smack headfirst into this. I try to write code that's as dumb as possible because that way I have a chance in heck of debugging it. So Kernighan's principle for lesson design is that we should teach practical computational concepts in the order of their debuggability. If it's easy to debug, teach the concept early on. If it's hard to debug, wait, because then they're going to spend most of their time debugging failed attempts to write code that does it. So for example, running shell commands in SnakeMake, super easy. You can run it inside of SnakeMake, and if it fails, you can also just copy paste the command at the command line. Does it work? Does it not work? Then you know whether the problem's in SnakeMake or the rule or the shell command itself. Wildcards. SnakeMake will output the rewritten rule for you when it's putting in place wildcards, so you can sort of debug things pretty easily that way. And then expand, you can debug with print. And then if you try and write SnakeMake workflows that distribute across a cluster, good luck, right? Because now you have a SnakeMake workflow interacting with Slurm or Torque or something else, and it's too many moving parts. So I have been unable to debug a number of things there. Okay, so that's my idea. I don't have anywhere clever to take all of this other than to say I hope these are useful concepts that have made you think. I'm happy to chat more about it. My concluding thoughts really are just that teaching workflow systems is hard, basically because you have to teach an abridged version of all of computing in order to get people to make sense of any of it. And then I think we should teach practical computational concepts in the order in which they can be debugged, rather than in some other principled order, like starting with Turing machines or something. And so basically, I think effective use and creation of workflows, it's a critical skill. We need to figure out how to teach it well. I don't think we're doing a great job of teaching it. If you have pointers to classes that have worked well for multiple people in your or somebody else's experience, I would love them. And I hope that's that, and I'm happy to distribute them. So I hope that was informative. And I want to end with one meme, which is sort of speaks to the whole situation, which is software documentation is often full of difficult jargon, and then the authors are like, "But why is nobody using my software?" And I feel that. So yeah, that's it. That's all I got. Hope that was interesting.